Why reality repeats itself. How infinite possibility collapses into a finite vocabulary of things. Look around and you see a universe that repeats itself. The same atoms form in distant stars and quiet laboratories. The same molecular bonds appear in interstellar clouds and living cells. Crystals grow with familiar symmetries. Waves interfere. Particles scatter. Vortices form in fluids, in plasmas, even in galaxies. Across unimaginable distances of space and time, the universe keeps producing the same kinds of things. This repetition is striking because, at the microscopic level, modern physics tells a very different story. Quantum theory describes a world of immense possibility, a vast space of states in which systems can exist in superposition, interfere, and explore configurations far richer than anything classical intuition would suggest. If almost anything is allowed in principle, why does reality look so conservative in practice? This is not a question about determinism. The universe is not rigid or predictable in every detail. Nor is it a question about observation or measurement. The patterns of matter and motion we see do not depend on anyone watching them. And it is not a question about design or purpose. The repetition of forms does not imply intention. It is instead a question about persistence. Why do some structures last long enough to shape the world, while countless others vanish almost as soon as they arise? Why does the universe record its history in a small, familiar vocabulary of stable forms rather than an ever-changing flood of novelty? The deeper puzzle is this. The universe is unimaginably large and old, yet its history remains legible. It does not drown in its own possibilities. Something limits what can endure, what can be written into the permanent record of reality. Understanding that limit is the starting point. Quantum physics invites a kind of vertigo. At its most fundamental level, it describes systems not as occupying a single state, but as inhabiting a space of possibilities. Particles can be here and there. Waves can overlap. Outcomes that seem mutually exclusive from a classical point of view coexist as potential realities. Mathematically, this space is vast, so vast that it is often described as effectively infinite. It is tempting to assume that such abundance must translate into equally abundant outcomes. If the universe permits so many possibilities, why wouldn't it realize them all? The answer is simple but easy to miss. Permission is not persistence. Quantum theory tells us what can exist, not what will last. Most possible states are fragile. They depend on precise coordination, delicate phase relationships, or sustained isolation from the rest of the universe. The slightest interaction, an exchange of energy, a stray collision, a coupling to the environment, can disrupt them. Possibility alone is cheap. Endurance is not. Most possibilities never progress beyond this preliminary stage. They flicker into and out of existence, suppressed by interactions, erased by noise, or dissolved by the system's own dynamics. They are permitted by the rules, but they are not realized long enough to matter. This distinction between what is possible and what is realizable changes how we think about the emergence of the classical world. The universe does not need to select among infinite options. It rarely even encounters most of them. Long before outcomes are fixed, possibility is already being narrowed, shaped, and constrained. The question, then, is not why the universe chooses certain outcomes over others. It is why the space of realizable outcomes is so much smaller than the space of allowed ones in the first place. When we imagine possibility, we often picture a flat landscape, a list of options, each equally available until something picks one. But the space of physical possibilities is nothing like that. It has shape. In quantum mechanics, the states a system can occupy form a structured space, and moving through that space is not equally easy in all directions. Some changes are gentle deformations, requiring little effort. Others demand precise coordination or large energetic cost. The difference is not a matter of probability or preference. It is built into the geometry of the space itself. Physicists describe this structure using the concept of the quantum metric. Stripped of mathematics, the idea is straightforward. It measures how different two nearby quantum states really are in physical terms, how hard it is to transform one into the other. States that are close can be interconverted with small perturbations. States that are far apart are effectively inaccessible without major disruption. This geometric perspective introduces a crucial shift in thinking. Possibility is no longer just about what is allowed by the rules. It is about what is reachable, given the structure of the space. Long before any outcome is fixed, the geometry of possibility already favors some paths and suppresses others. Nothing is choosing among alternatives here. Geometry does not select. It simply defines distances and resistances. It determines which transitions are natural and which are prohibitively difficult. The consequence is profound. Even within an enormous space of theoretical possibilities, only a small region is dynamically accessible. Most paths are so steep, so fragile, or so finely balanced that they collapse under the slightest interaction. What remains is not a random sample of what could exist, but a compressed subset shaped by geometry alone. By the time irreversibility enters the story, the space of viable outcomes has already been dramatically reduced. At this point, a deeper question emerges. Why should the universe compress possibility at all? Why not allow every allowed configuration to leave its mark, however briefly? The answer has nothing to do with elegance or efficiency. It has to do with capacity. A universe in which every microscopic possibility became part of lasting history would not be rich. It would be incoherent. Records would overwrite one another faster than they could stabilize. Structure would dissolve into noise. There would be no persistent objects, no reliable patterns, and no accumulation of history in any meaningful sense. For anything to endure, change must be selective, not in the sense of preference, but in the sense of constraint. Persistence requires that most fluctuations fade without consequence. Only then can a small number of outcomes stabilize long enough to shape what comes next. Compression, then, is not an added feature of the universe. It is a prerequisite for history. Seen this way, the familiar structures of the classical world are not the result of fine-tuning or cosmic bookkeeping. They are the survivors of an enormous narrowing that occurs before irreversibility ever takes hold. Geometry limits accessibility. Dynamics eliminate instability. Only then can lasting records be written. The universe does not manage infinite possibility by tracking it. It manages it by never letting most of it matter. If the universe repeatedly produces only a limited set of enduring forms, what defines that set? The answer is not a single principle, but the intersection of several constraints that act together. The first is symmetry. The laws of physics enforce invariances. The same experiment performed here or there, now or later, yields the same result. These symmetries do not dictate what must exist, but they forbid vast classes of structures outright. Only forms compatible with these invariances can recur. Symmetry removes most of possibility before dynamics even begin. The second is locality. Interactions propagate through contact, fields, and signals that travel at finite speed. Any structure that requires global coordination or instantaneous influence cannot be assembled or maintained. Locality favors forms that can be built, stabilized, and repaired through nearby interactions alone. The third is conservation. Persistent structures must respect budgets. Energy, momentum, and charge cannot appear from nowhere or vanish without consequence. Structures that require continuous, unbalanced input, or that amplify themselves without source, are short-lived by necessity. The fourth is dissipation. Irreversibility does not create structure. It destroys unstable ones. Any enduring form must absorb disturbances, shed excess energy, and relax back toward stability. Structures that amplify noise or depend on perfect isolation are erased almost immediately. Together, these constraints define a narrow region of possibility. The result is not a catalog of predefined designs, but a finite family of survivors, structures that can be repeatedly formed, perturbed, and reformed without falling apart. At this point, it is tempting to speak of templates, but this word must be used carefully. There are no blueprints stored in nature, no instructions waiting to be consulted. The templates that matter here are not prescriptions, but equivalence classes, names we give to families of structures that repeatedly survive the same constraints. Atoms are not copied from a master design. They reappear wherever conditions allow because there are so few ways for matter to organize itself stably. The same is true of molecules, crystals, quasi-particles, waves, and collective modes. These forms recur not because they are favored, but because unfamiliar ones almost never persist. Repetition, then, is not a failure of imagination. It is the price of endurance. So far, everything has occurred before anything permanent happens. Geometry compresses possibility. Constraints eliminate instability. A small family of robust structures remains. But none of this, by itself, creates history. History requires irreversibility. Irreversibility enters through dissipation. Energy spreads. Correlations decay. Information about precise configurations is lost. Once this happens, the system cannot simply return to where it was. The past constrains the future. Irreversibility does not choose among infinite possibilities. By the time dissipation leaves a permanent mark, most possibilities have already been excluded. What remains are stable structures capable of absorbing the cost of change without disintegrating. The classical world emerges from this accumulation of commitments. It is built not from everything that could occur, but from what can survive the cost of occurring. The universe does not remember everything it tries. It remembers only what lasts. Many explanations attempt to account for this order. Some appeal to selection, others to observation, others to chance multiplied across vast ensembles. Each captures part of the picture, but each begins too late. The perspective developed here operates earlier. It does not ask why a particular outcome occurs, but why only certain kinds of outcomes ever persist. The answer lies in constraint, not choice. Geometry shapes accessibility. Conservation limits affordability. Dissipation removes what cannot stabilize. This explains why classical reality scales. The universe can be vast without becoming unintelligible because it does not have to record everything. It records variations of a small number of stable forms. Nothing is being optimized. Nothing is being selected for success. Instability is simply erased. The insight stated plainly is this: the universe does not produce a stable, intelligible history by choosing among infinite possibilities. It does so by ensuring that most possibilities never matter. Long before irreversibility occurs, geometry and constraint compress possibility into a finite vocabulary of stable forms. History is written only in that vocabulary. Infinite possibility exists, infinite realizability does not. That asymmetry between what could happen and what can endure is what makes a coherent world possible at all.